All right, begin.
So we're going from the progression from finding a simple limit, then to evaluating the derivative, and then to eventually the end goal, finding the gradient of a scalar function. So to define the derivative, or at least the notion of a derivative, we have to understand what a limit is first. And to understand what a limit is, we have to understand continuity and just what a function is as a whole. So if we've got a function as such of, let's say, 1 over x squared, it looks something like this, right? You've got a vertical asymptote at x equals 0 because, well, we'll do this at x. We have a vertical asymptote at x equals 0 because it's undefined at x equals 0. So this graph is not continuous. So what we have to resort to doing is finding the limit as x approaches 0. So here the graph is coming from the left, all right? Which we can denote by doing the limit as x approaches 0 from the left of f of x, which in this case, because the graph is going to positive infinity, would equal infinity. Whoa, would equal infinity. And the same concept goes with the right side, where we're looking at it, and the trend is that it's going to positive infinity. So the limit as x approaches 0 from the right of f of x is also infinity. And because the left and the right side are equal, we can then define this infinity as our general limit. So by using point A and point B, right, we can establish, which both these imply, that the limit as x approaches 0 of f of x equals infinity. All right, so now that we have like an understanding of limits, we can now apply this. So we've got this wacky statement right here. The limit as h approaches 0 of f of x plus h minus f of x over h, which initially seems like a very foreign, out of the blue concept, but it's actually from a very familiar algebraic equation that you're given of y2 minus y1 over x2 minus x1. Firstly, we can rewrite this. This top right here can be rewritten as f of x2 minus f of x1 over x2 minus x1. Alright? And in this case, we're letting x2, we're going to represent x2 as a very infinitesimal increase in size or in distance from x1. So if we've got this graph of x squared, the difference between right here at, let's say, 2, and the difference between here at, we'll write this as 2.0001, it's so tiny that it's nearing 0. So what we can do is we can write f of x plus h, where h is some tiny increment that is infinitesimal, it's infinitely small. So we're really getting close to approximating what this value is at 2. And what we're doing then, if we know this formula here, if we know what this is the slope. And essentially what the derivative is just approximating the slope at an individual point instead of approximating it over a long area. So we can take the derivative of this and plug things in. So we'll stick with x squared for this one. So we have the limit as h approaches 0 of f of x, which is x squared. And we plug it in here. So we have x plus h squared minus f of x, or x squared, over h. So now it's just a matter of factoring and doing math. I mean, seriously. But this is boring. We don't want to do this. Instead, we use our power rule, and we just do this. If we take the derivative of that, you take down the exponent, and you end up with 2x. Wow, there's the derivative, which this means we have an approximation of the slope. So now, on any point of x squared, we know that the slope of this graph x squared is proportional to 2x, right? So if I have 2 at slope 2, right, at point 2, it's going to be 4. If I have it at, evaluated at x equals 3, we've got 6. And the slope is always increasing as we get an increased value, and we can figure it out by just plugging it into the derivative. So that's a very simple idea of the derivative. And now we kind of increase it into something called a vector field. So we're given a blob. We'll use this little blob here. We'll define this as a vector space B. Okay? And we want to define this function, the derivative, that takes something from a polynomial of, for this case, we use P2. So all polynomials of degree 2. And this function derivative takes it this doesn't work. We'll take the derivative of this vector space B, and it brings it to some point in R, the real numbers, which is just a scalar value. So it'll be 2, it'll be 3, it'll be 4, any number. And what we're going to do is we're going to find something called the tangential vector space. Well, we'll represent this, so we've got a little box here. This is the tangent vector space. And we've got a point P right here. And we can write this point P as the tangent vector space P, right? Yeah, and then this is a dual vector space, so it's got a little star. And this is where our vector field is defined. This is really where we get this essence from. We've got a vector, we'll define some vector on this tangent vector space P with a vector. And essentially what we're doing is saying that on this tangent space, we can define the vectors for the entire vector space, D. And on this vector space D, we just draw out some arrows. Here's our vector field. So all these vectors kind of are represented. And if we have another tangent vector space, let's say Q, right? Q right here. TQ, it could have a different set of vectors. Like let's say it's going this way. And what we can do is we can actually add these vectors up and they kind of make different little shapes, and it can be pretty cool. Fundamentally, this is what the idea is. This is assuming a Riemannian metric, so it's, a Euclidean metric, so it's kind of simple, but that's a constant. Now, if we actually want to take the gradient in application, the gradient is taking a scalar value function, so it's not a vector, it doesn't have direction, it just has magnitude. We'll define that with f of x. Right? Which we'll just shorthand as f. If we want to take the gradient of f, okay, what we're going to do is we're going to take the partial derivative of f with respect to x, and then we're going to multiply it by the first basis of our vector space, E1, and then we're going to add, well, for this case, assuming R3. So we have 3 bases for R3, E1, E2, E3. I don't think I have to define these for you guys, but we've got del f, del y, E2 plus del f, del z of E3. And essentially what this is doing is this is taking our scalar function f and putting it into a vector. And what this vector is doing, letting us do, is make this vector field. And this vector field is allowing us to visualize what the derivative was. It's letting us find the slope. And this is applicational in a lot of situations. Let's say I'm on a planet, and I've sent this robot on this planet, and the planet's got this real wacky geometry. It's got like a plane here, and then you've got like mountains, right? Like a topological map, right? It's got little mountains here. And it's all over the place. And we want this robot to find, that's the altitude, right? On the flat surface, it's pretty easy because it's fully consistent. It's essentially continuous. With the gradient, and what it allows us to do is, as we change in our x, y, and z coordinates, we can figure out this rate of change on those certain particular points. So it's very applicational for non-Euclidean geometries. It's very applicational for funky shapes. And it does end up being applied in areas such as physics, and I think the most glaringly apparent use of it is just in the formulation for for force, where you have force equals mass times acceleration. Any simple physics students know that this is equal to the derivative of momentum with respect to time. But a little bit lesser known is that force is actually the negative gradient of potential energy, which I'll use U for. So we can use the negative gradient of the potential energy to find the change in momentum, which allows us to calculate our force. This is very helpful in Lagrangian Hamiltonian mechanics when you're dealing with a phase space. And I think that's really the essence of differential calculus. I think being able to find these different rates of change for different values, different geometries, different functions, I think it's a very useful skill that everyone should know. Thank you.